So thank you for joining everybody. My name is James Christ. I'm one of the senior application engineers at EnginSoft. So I support some of our RecurDyn customers as well as a few of the other products we carry. So high level overview of what we'll be going over today. I'll do a brief introduction about who EnginSoft is for the folks who are new on the line. Then I'll do a brief introduction on RecurDyn. Again, I know we have quite a few existing customers, so that'll be a little redundant, but for all the new folks on the phone, be good to have a high level intro. And then we'll jump into the meat of today's presentation, talking about fatigue and durability. I want to do quite a bit of the essential concepts, kind of going over the background theory before we jump into a brief live demo of the software. And then we'll wrap up with a Q&A session. A little bit of kind of admin stuff. So there's a chat window and a Q&A window. If you move the mouse around on your screen, you should see a bar at the bottom show up, and then you can put questions in either of those spots. This presentation is being recorded, so if you join later, you have to leave early, that recording will be made available. So kicking off with who EnginSoft is. EnginSoft USA is a part of a multinational company that was formed in the mid 80s by a group of engineers in Italy, and they've since expanded out, but have stayed true to their core focus of CAE technology. So today we have over 200, and that might be over 300 at this point, experts in technology across a wide array of CAE topics. And we're leaders in virtual prototyping and optimization. And we provide customized solutions and some of the leading innovative technologies to our clients to help them solve complex problems. Our strategy is the harder the problem, the happier we are. These will pop in. So since founding in Italy, we've since expanded across Europe and into North America. So we've got the US office in Dallas, and then we've got a wide array of offices across Europe. Here are a couple of customer logos by industry. So this covers all of EnginSoft, and I'm sure you might see your own logo here, and you'll probably see some familiar faces. Yeah, so we've done over 4,000 consulting projects globally. We have over 1,500 software customers, and we do over 130 trainings every year, specifically to customers or more general product-based trainings. We've worked with academia on over 60 academic projects. So you can see some of our core competencies popping up on screen now. So obviously we're focusing on fatigue and durability today, but that plays into a lot of other topics as well, including HPC, optimization, cyberoacoustics, multi-body, obviously. With that intro out of the way, let's jump over to about RecurDyn. So this is just a few slides to set some baseline. So yeah, so the vendor function bay, they're the ones who actually create RecurDyn as well as MFBD for Ansys, which is a plugin Ansys Workbench using the same solver. So this is a South Korean company. They've been around for over 20 years, and it's like the kind of classic story with CA software tools. It was born out of academia and then was commercialized, and those original developers are still involved. So there's a global network, including Korea, obviously, and then Japan, China, India, Taiwan, the US, and then several supporting offices in Europe. Connections with other third-party tools. So KISSoft, you've probably heard of before, as well as EDEM and ParticleWorks. These are for very specialized types of analyses. Moving on, some of the customers. So we have over 500 customers globally, and again, you might see your logo or other familiar logos on this page. little bit about what makes RecurDyn unique in the marketplace. So it's a multi-body simulation platform, and we really mean it's a platform. So because it can connect with other software tools, um, sort of act as the central model that you have, and then you can plug on other physics to it. Now, obviously, we do classical MBD, rigid bodies, joints. That stuff is complicated to do by hand, but pretty much every software tool can do it. Where RecurDyn really differentiates itself is with support for flexible bodies, which we'll be talking about quite a bit today. And then it's technology for contacts. So it can handle a very large number of contacts, um, and both using their general geosmoothing algorithm for kind of generic contacts that'll work on anything, and a huge array of analytical contacts for specific use cases. Going back to the flexible body pieces, so we have two modules for that. We call them reduced flex or R flex and full flex or F flex. And the difference between those two, reduced flex, you'll often see in other tools called Craig Bampton or CMS. And this is kind of an industry standard approach, taking a linear modes analysis. So you sort of compress down information about a linear flexible body, and that's computationally efficient. So there's limitations with that. You can't really do contacts with it because you're approximating it as a superposition of linear modes. So there's limitations on what you can do with it. Whereas with our full flex technology, this is really essentially embedding an FE solver into an MBD solver. So we can do contacts between flexible bodies, contacts between rigid bodies and flexible bodies. That whole matrix there we can cover, nonlinear deformation, nonlinear materials, all that sort of stuff, using our FFlex module. We've already touched on the interfaces, so one I'll point out right here, this is showing a co-simulation with a particle CFD tool called ParticleWorks. You can do this as a one or two-way coupling, and you know this is the kind of analysis that would be difficult to do with any other tool. You have so many bodies here, so many contacts, and then the coupling with fluid. It becomes a very complex problem, but relatively simple to set up in ParticleWorks and RecurDyn. And just going a few other key features that are worth talking about. So the solver is very robust, handles both low and high frequency domains, and it's excellent with large models. So we have a lot of customers doing track models or chain models where you've got 100, maybe over 1,000 links in those chains. Then for flexible bodies, you end up with very large models, because every single element has to be tracked throughout that transient simulation. An example of a very complex flexible body simulation here, the deformation of a CV boot joint or CV joint boot, and this is comparing with test. There was very good agreement with that project. It's also customizable, so I think this is a huge win for any CAE tool. Um, do a lot of scripting and automation work around your specific processes. We have CAE support globally, and we've got a huge network that we can lean on to get the expert in your domain on the phone when you need it. And then this is the last slide on the intro. So I just wanted to give an overview of kind of functionality. So it's a very modular platform, and RecurDyn Professional is sort of the base module that everything else uses. And all the contacts and joints and all that stuff. And then we can plug on different functionality. We separate that into sort of three functional groups: toolkits, extension, and interfaces. So the toolkits are really using the core solver and then adding automation to it. The most clear example of that is with the track and the chain toolkits. So if you think about setting up a track model, you've got like a tank, and then you've got the two tracks. Setting that up by hand would be extremely tedious, right? You've got all of these links, and they all need to be connected to each other. You need to define contact between the links and the ground and maybe other components. So RecurDyn has basically automated that entire process where you can define, hey, I need a sprocket here. It's got these parameters. It'll make the geometry for you, and then you connecting this sprocket and these four road wheels, and that's going to define the track system, and it'll do the wrapping and placing of all the links for you and all that stuff. And then for extensions, these actually add solver functionality. So we'd already talked a little bit about rflex and fullflex. These are adding, flexible components to the model. Then we've also got a controls library. That's this colink here, and auto design for optimization. Quite a few other things. We also have a mesher built in, so you can either use an external mesher and bring that in, or you can use the built-in one, whichever is easiest. I have interfaces, like I mentioned, to other software tools. So all of our CAD reading libraries are included in this, and then interfaces to ParticleWorks, for example, or EDEM for a DEM simulation. On the CAD, I will mention that we do have a special interface with Creo for anybody who's a Creo user. So that'll handle importing and updating, keeping your geometry up to date as you're working on the model with other people. Let's go ahead and jump into the meat of today's presentation. So in this slide deck, we'll be going through, like I had mentioned, sort of the core concepts behind what fatigue analysis is, how it works behind the scenes, so you have a little bit better understanding. And then we'll go into the actual implementation in RecurDyn and do a live demo kind of showing what the process looks like. Depending on time, we can go through these applications in very little detail or a little bit more detail. Obviously, there's a Q&A session at the end. So starting off with, when it comes to fatigue, I think it's easier to take a step back and talk about fracture mechanics for a brief second. So we're in an ideal world where everything is a sphere in a vacuum. To the stress strain curves, and these really represent static loading. So idealized, but they're very useful. And we can talk about some of the components of the stress strain curve. We've got our elastic region, our yield stress up at the flexion point here. As we keep adding load, go through this plastic deformation region to our ultimate strength, and then finally the fracture point. So like I said, this is a static type of analysis, and it can be used for kind of back of the envelope math, but there are scenarios where this doesn't give you a good answer. One of the reasons for that is that we sort of idealize this region as being perfectly elastic, but that's not really true, right? So if we think about what this yield strength represents, it's actually defined as being the point where when we release the load, we have only 0.2% plastic deformation. So that sounds like a very small amount, but as you keep applying that load cyclically, we're going to keep adding plastic deformation on top of each other. Eventually, that product is going to break. And that's where fatigue comes in. So when you have repeated loading, the static yield strength is kind of a useless metric. Because we don't care if it fails on the first cycle, we care if it fails on the millionth cycle. So we need some way of sort of quantifying that. We do that through this fatigue analysis or durability analysis. They can really be used interchangeably. And we think about things in terms of fatigue life. So how many cycles can something go through before it's going to fail? And to sort of formalize that, we have this SN curve. We'll come to in a second. And we can use this type of analysis to look at not just very simple sine wave repeating loads, but irregularly repeating loads. So like I mentioned, we use this SN curve as our sort of criteria for evaluating whether something is going to fail too soon or too early. And really the importance of that is when we're thinking about like warranty claims. That's sort of the uh, thing that the accounting department cares about, right? So that becomes one of our constraints. If we know this needs to be in the field for 10 years and we know that it's going to be spinning at 500 RPM, for example, we can figure out how many cycles is this object going to experience, and if our warranty goes out through 10 years, we need to make sure that we have a high confidence it's going to actually last that long. Only we can't spend 10 years testing that. So what we can do is use the use material tests to figure out what our expected number of cycles is. Look at these two graphs. We're looking at an idealized um, load over time. So we've got some stress and there's a mean value, but it's oscillating about this mean value. You can think about something spinning at a steady rate. It's going to experience this cyclical loading. Then these are going to correspond to some point in this SN curve, which is showing us the what the alternating stress is, and then the number of cycles to failure. And this is on a log plot. We don't necessarily care if it's going to fail at 1,000 or 1,500, but we need to know if it's going to fail at 1,000 or 10,000 cycles. And we see all of these little dots showing sort of material tests. So, you would send this, sample of the material. Let's say it's some steel. You would send that to the testing lab. They'll run a bunch of tests and then draw a nice clean curve that we can use later on for making design decisions. We're thinking about this SN curve and sort of where our product is fitting into it. We'll break it down into low cycle and high cycle regimes, and this comes into play later on as we're making assumptions about how we're evaluating a particular part. But low cycle, less than 1,000 repetitions uh, for failure. So this is something that you're not talking about a shaft that's going to be spinning for 10 years. You're talking about something that you don't expect to experience a ton of varying load. Then there's the high cycle. So this is something that you were talking about, millions of repetitions. We needed to survive that long. The head of the animation. And for the folks that either noticed this or remembering this from college, um, there's this infinite life or a fatigue limit. So you can see that this curve is steadily dropping down. As we decrease the oscillating stress, the part will last longer, and then at some point this curve levels out, depending on the material. Some materials don't have a fatigue limit, um, but at some point, so for example with steel, if you have a loading below some limit, then it'll never fail. At least assuming there's no defects. So when we're talking about something that we're expecting to be in the infinite life region or regime, then talking about the SN curve becomes a little bit less useful because we care more about what our margin of safety or safety factor is versus where we're lying on the SN curve, because we expect to always be below the fatigue limit. And that's where this Hague diagram comes in. So it's showing our effective stress here and then the ultimate stress. Um, we have a safe region on this side. So if our oscillations are below a certain point and our mean stress is below a certain point, then we're going to be safe. And if it's above those, then we're in this failure region. And ultimately what we care about is how far into this safe region are we, and that's going to define our safety factor. Talking a little bit more about this Hague diagram, um, think about how it's actually being generated. I think that's helped me understand like why that curve looks the way it does. So if we think about sending off a bunch of samples to a materials testing lab, um, and then they run a bunch of tests, so they're looking at varying both the mean stress and then the amplitude of the stress. So in this case, we have oscillating about no stress. So oscillating between a pure tensile and pure compressive stress, uh, averaging out to zero, and that's going to have some point on this curve lying on this line. And as we increase our mean stress, we'll be decreasing our stress amplitude and plotting at what point these samples are failing. And if you do that, then you end up with this basically straight line um, showing that if we're below this line, then it's not going to fail. If we're above this line, it is going to fail. One thing that's worth pointing out, so you can see that the slope of these lines is very different. So the compressive behavior is much different than the tensile behavior. Tensile is almost always going to be the primary driver of failure. Um, we have a different scenario that's at least worth keeping. Now, this is great if you can send off 1,000 samples to a testing lab, um, but oftentimes it's more convenient to use some of the relationships or correlations from literature. And so what these are doing is taking some known material properties like the ultimate stress or the yield stress, um, and using those to approximate what the Hay diagram is going to look like. There's different correlations for doing this. So you can see a couple of these names here: Gerber, Goodman, Morrow. And these are going to be dependent on kind of what type of material you have and what loading conditions you have. I'm not going to go into a ton of detail on those, but a thing that you would look up when it's time to run the analysis. So what are we doing when we're actually calculating the fatigue life? So we're taking this stress amplitude and then looking at the mean stress. And for example, with Goodman, um, we're combining these, taking the stress amplitude and the mean, um, and then solving for the effective stress. And that's going to give us a position on the SN curve. And we can draw that over to get our expected failure. And now we can introduce this concept of damage. So instead of talking about it in terms of this, actually communicating about these things, it's much more convenient to think in terms of damage and fatigue life. Those are just two sides of the same coin. So you can think of damage as the amount of use life that we get from each cycle. Uh, and our fatigue life is then going to be 1 over the damage. So fatigue life is the number of cycles that we expect the part to last. So far, we've been talking about these very simplified, um, realized cycles, but in reality, the real world is never that convenient. So we end up uh, with load cycles that look more like this, right? Where we've got a highly varying load, and to actually convert this back into something that's useful, we do something called rain flow counting. Probably remember this from college. And basically, what we're doing is turning this or taking a subset of it, turning it on its side, and then saying, okay, we're going to count every time that we change direction. You actually draw it out, then it looks like rain falling off of water feature, basically. And by looking at each one of these individual components, you can sort of break down a very complicated problem into a bunch of really small problems, solve those, and then bind them back together at the end. What we're doing is for each of these rain flows, um, we're converting that into an idealized version of an input cycle, and we can solve for the on each of them independently. That and then kind of plot each of these onto our SN curve, and we get some amount of damage from each of them. We've got the damage from the first input cycle, the second, third, on to infinity. Because this has sort of been linearized, it becomes easier to combine those back to a total fatigue life. So essentially, this is what the software is doing behind the scenes, um, but it's a very tedious process. So it's nice that we have computers doing it for us. And at the end of the day, this is kind of the output that we're interested in. So I got ahead of the slides again. Another way to visualize this, and we'll see this later on in the outputs that RecurDyn is able to give you, new sort of a 3D plot to visualize what this rain flow counting is doing. You can sort of lump together the flow analysis. So you can see this is mean over here, mean stress, and then the range. So we're taking some portion of this random stress signal, and then give us a number of cycles for each of these curves here. The point of looking at it like this is you can sort of see, okay, my primary impact is coming from a cycle at this frequency or at this frequency. That's what I need to focus on. Just sort of not having anywhere to focus your energy. So next, we're going to kind of continue down the idea that what we've talked about so far is idealized world. So we're doing these when a materials lab is doing the testing. They're assuming that you have perfect samples, right? In reality, that's never the case. So we can apply corrective factors to our SN curve to account for things like stress concentration zones or the effect of well, I'll go through these pretty quickly, but basically you can apply some factor to the SN curve to get a modified or a corrected SN curve. Then you use that for evaluating your lifetimes instead. Notch factor, this one is really the fatigue version of a stress concentration. Uh, and to actually get the factor, you would look this up in a table basically to figure out what's an appropriate factor for your problem. And moving on, I won't go through all of these in detail. Like I said, these are pretty much things you would look up in a table in real life. But things that can affect the fatigue lifetime surface finish. So if you have a rough surface, your fatigue life is going to be lower. Same thing with size. So if an object is larger, there's an increased chance that there's defects in the material. So you can compensate for that with a scaling factor. And similarly for loads, different types of loads can apply different factors. And then, like everything, we have sort of a catch-all other section. So if you had, effects from temperature or things that you knew from physical testing, you could apply those as another extra term. But at this point, so now we'll go more into kind of what you would be doing in the software to perform this analysis, right? We've talked about the background theory is, but at the end of the day, you need to give your boss a number on how long this thing is going to last. So, so when you actually go into the software, there's various different methods that you can use. Like we had talked about the Gerber or Goodman, those sorts of things. So there's a huge array of different correlations that you can apply depending on the uh, type of model that you're doing. So for a generic high cycle evaluation, Mason Coffin is the default. For different scenarios, you might choose ASME or this weld model. Looking at low cycle type problems, like how we had talked about low and high cycle regimes, or for low cycle scenarios, it's better to use strain for approximating the life. Those are those can deal with plastic deformation. And there's different correlations as well for doing safety factor. Over this, we'll see some of this again when we jump into the software. I'll just kind of mention the different life criterias are basically using different coefficients and exponents, solving all of these backend equations. Now, when we actually jump into RecurDyn, you can choose to use a default material. So there's a big material database that we'll see, or if you have a custom SN curve, so maybe you already have material lab data that you can use, um, plug that in either from a CSV file or if you're just manually typing it in, they're both possible. Similarly for when you're looking at safety factor, um, give you the hay diagram where you can put one in manually. So next we'll kind of give a high level overview of what the procedure is. So you'll run some flexible body analysis. Um, Glossing over that part today, but I think we've done webinars in the past talking about falling. We're going to, so once we have the stress strain history data, then we can do this. Everything else is a post-processing step. So that's one thing that's kind of important to note. Um, for doing for the purposes of durability fatigue analysis, you just have to have results data. But everything beyond that is post-processing. So you don't have to know ahead of time that you're doing a fatigue analysis. When you have this time history, what has to be done is what's called a tensor transformation. So to explain on the next slide, when we do this tensor transformation, what has to happen is we're interested in the stresses on the surface of the part. Because in reality, cracks are always going to form on the surface, but internally. So we have to convert our FE results from per element stress strain to a surface stress strain. And then the other thing that has to be done is calculating this maximum damage direction. And just to clarify one thing before we keep moving on, this is all really handled behind the scenes for you. It's just helpful to understand what some of the options are telling the software to do. So we have to calculate this maximum damage direction. So essentially, if we think about this little node here, doesn't know which direction are the principal stresses. So it has to basically check all of them. Basically do a sweep over 180 degrees to see, okay, this vector is where my peak damage is coming from based on the stress time history. So we can kind of see all of these increments or steps, basically checking, is this my maximum damage direction? No, move on to the next one. And it's going to basically do this sweep, find this highlighted red vector. So moving on, it's worth talking about the difference between uniaxial and multiaxial stress, and this plays into some of those correlation models as well. So again, the idealized form is a uniaxial loading condition. So I like to think about this if we have, those material test samples and we're just applying a load up and down to see when it breaks. That's very clearly a uniaxial problem. Rarely does that happen in the real world. So more often than not, we have multiple axes that need to be considered. The next approximation is a biaxial stress. So this you've got two primary directions, and then triaxial you've got three. In reality, when we're looking at the surface of an object, then we can sort of discount the triaxial axial stresses. So we're basically always choosing between assuming a uniaxial stress and assuming a biaxial stress. Um, so when we do this biaxial, I convert the the stresses that it finds into primary directions, 1 and 2, and then got basically special cases of this biaxial ratio. So we've got this ratio here is equal to 0. That corresponds to a uniaxial load. Uh, there's no secondary component, and then you've got the perfectly biaxial where you've got both primary directions have an equal loading. In general, you are going to be somewhere in the middle. But one sort of important thing to note is we're doing this biaxial assumption, uh, generally assuming that these are relatively similar. So if you have a scenario where one one direction is primary, then it does make more sense to use uniaxial. Uh, Biaxial will give you a more conservative. Um, so at this point, I'm going to switch over to the software. So for any of the current customers, you may recognize this model. It's one of the tutorials for doing durability. Um, for any of the new folks on the screen or on the phone, I'll do a kind of a brief. So we've got our main modeling window here. There's 2 tabs open. This is a demo, so I've got the the backup pre-solved or pre-computed results in case I fat finger something. You can have multiple windows open. And on the right-hand side here, we have our model tree. We call it our database. Um, there's a couple of components here. There's this tire, this shaker table, um, and then there's a bunch of joints defining connections between components and a few bushings, which are forces. Into parametric points today, um, but you may notice that there's a bunch of stuff in this model that's not showing up in the bodies here. Um, these are what we call subsystems. So these are the direct equivalent of a CAD subassembly. Uh, they help with model reuse. So if I wanted to use this suspension assembly somewhere else, um, save something as a subsystem, and then import it, it can sort of also help keep your model tree clean and organized. So we've got a pre-solved model. Oh, actually, I remember the. So what's happening in this model is we're shaking this table using expressions. So you can see on the right-hand side here, we have this rotational joint uh, shaker table. Um, is basically defining the motion. So that's what this little, it's got a slightly different icon. That means there's motion applied to it. This thing is moving up and down, and that's being driven by some expression here. So it's basically a sine wave, and then this step function is ramping us from a magnitude of 0 to a magnitude of 30 over 1 second. I don't have to know how this is all organized, but I just wanted to give some background on what's happening. We can play it back. So it starts off with a super low amplitude, and then it's ramping up over time. We've got 1.2 seconds of simulated time, including these 2 meshed bodies. So uh, you can basically think of them as FE bodies that are being solved in a transient simulation, and they're connected to rigid bodies where the deformation doesn't matter. I also notice this sort of looks like a mesh body. In case it's not, so I'll actually jump. So this is actually just an idealized spring. Waiting for that. Okay. So this is just a simple force. But we do have a spring toolkit that's also available for more complicated springs when you um, have a linear spring out of this subsystem. The first step that we have to go through when we want to do a durability analysis is define what we call a patch set. So basically, we need to tell the software these are the elements or the faces that I want to solve durability problem on. They are both inside of a subsystem, so I'm going to use this navigator we have to quickly jump into those. We've got our upper control arm and a lower control arm. The upper one today, let me move in here. What these do is define a patch set. All right, so add everything. Come back to the top level of the model. And this one is mostly for current users that want to try this later. Um, you'll notice that the animation results get wiped away. Um, basically happens anytime some change is made because it isn't positive that the previous results are still compatible with the change. Uh, just add a patch that doesn't affect the results, so you can just reload the animation using this button here. This still plays back. Cut that off early. So next step is to go into this post-analysis tab. So we've got this ribbon interface here, and it largely organizes by functionality. All these post tools are here. Different toolkits have their own section. So make a chain subsystem or a belt subsystem engine. Not doing that today. So for our preferences really quickly. So this is where you can address some of the calculation methods that are being used. So we had talked about the fatigue factors that can play to the results. Leave these all at default. I just wanted to show where you would go and change those if you needed. Go into fatigue. All right, so I'm going to leave these at basically the default. They're appropriate for this model. Um, in this case, we don't have like a rotating shaft or anything. The stresses are pretty much all in the same direction. So I'm using the uniaxial, but biaxial just by changing this rate. Already it's still 10 to be the menu. Showing up off screen, but we can at least take a look at the SN curve. So you can always do a sanity check, and this is probably more important when you have a custom defined material. You can preview what the SN curve looks like for your given material. We obviously need to tell it which patch we're interested in. Uh, we can select something from inside a subsystem by just shift as we're selecting it. Selected that patch set. We can select time histories. In this case, we're just going to use the entire time history, and we're going to say that this happens a million times. That's basically it. So we'll go ahead and do the calculation. This is purely post-processing, so it doesn't take a super long time. We also used a fairly large searching increment for finding those principal. So now we get some sort of summary information about the max damage and the minimum lifetime. Being a very large number here, which is generally okay. It's a lot easier to view these results as a contour versus numbers. Windows has a great habit of placing windows off screen. So in this case, we'll keep this at contour, and we can go ahead and view what this looks like. So we're seeing a very kind of, we're not seeing a ton of detail in this, um, and that's mainly because we don't have the log scale turned on. So let's enable the log scale. Now we have much more meaningful results. Right now we're looking at the damage line. So on the inside where it's going to have while stress is applied, there's a lower damage there, and then where the bending stresses are the maximum, see these higher damage values. Everything looks like a very small number, which is a good sign. And click OK here, and we can also calculate the lifetime. So we now see where our lifetime is basically an inverse of the damage plot, which makes sense. We see that our minimum value has a very large exponent. So this part is probably fine. You actually go through the tutorial later on. Part is not okay. For the point of the tutorial to show you, okay, this part is good, and this one needs some work to not be a huge problem with warranty claims later on. And I think the last thing I want to show while we're here, contour and damage vector. You can also view those damage vectors around and see that these generally make sense to us. They look like they're in the direction of bending. So with that, let me switch back to the slides. Jump past a bunch of these, which we've essentially covered. One thing that's in these slides that's pretty good. So in this example model, the preloading actually needs to be considered, and you may have seen there was a checkbox for pre-stresses. So if you have like a press fit component, then you need to take into account those internal stresses. Those are basically going to act as an offset. They're going to statically increase the mean stress for all nearby elements. Basically, there's instructions here for doing it. I won't go through the whole process. There's significant difference that mean stress is being shifted up. Apply the preloading graphically. That okay, this part looks fine. Now, not as much. Uh, uh, a little one next to the chat icon. Thought we had a question, but it was just Alana asking if there's questions. Yeah, so we've got about 10 minutes left in the session. If you have any questions, please put them into either the chat window or the Q&A. We're keeping an eye on both. Let me jump through a couple of these examples that we have prepared. Yeah, so I wanted to talk about the random vibration test and the ESG that we can do, because these are both kind of on certain scenarios. So you might not have a known input loading. There might not be good reference data, for example. Want to sort of do a frequency sweep and figure out where might I have issues and what kind of frequency ranges should I be concerned about, and make sure that we're designing away from. Do that with a random signal. So essentially telling the software I want a random signal in about this point, and it'll sort of do those tests for you. Without going into all of the signal stuff, because I'm a mechie, we can basically generate a spline that gives input data for generating a random signal. And we have a function. There's a ton of built-in expressions in RecurDyn. In this case, we're using a special function for taking a corresponding spline or an appropriate spline, and turning that into the correct input signal for an object. Uh, Basically, we can find a spline and then apply that as an input signal. Though I will mention here is if you're doing something like this, you need to make sure that your reporting interval is appropriate. So if your output frequency is too large, then you're going to be missing data. Basically, this is called the Nyquist. You need your re- reporting frequency to be less than this value to be sure that you're capturing all of the results. Yeah, and then so we can do this fatigue analysis. I can jump back to the software and show you where the output for this is. We can see, okay, what is happening with this input frequency, and where should I be concerned with, where damage is happening. The other one I wanted to touch on is this TSG. So I got somebody mentioned that my audio is cutting out. Alana, is my audio okay?
So it is mostly okay from my end. I do not, there is a little bit of cutout. It's kind of like when you're on a Bluetooth where it gets quiet between words.
Okay.
But so far I've
I
got
moved my
every,
mic a little bit, so
okay.
okay. Is SN curve applicable when sample is subjected to pre-stress? Yes. So let me jump back. Yeah, and the question might have been asked before I got to this slide. So when you have a pre-stress applied, it's effectively just shifting your mean stress, but your amplitude is staying the same. So in that sense, you are just sort of shifting where on the SN curve you are, but the SN curve still applies. You are above Goodman. You calculate fatigue life. So Harsha, let me follow up with you offline. I'm not sure getting the question. So the question is, if you're above Goodman, above the Goodman curve, how do you calculate fatigue life? And we might need to have a little bit of back and forth on that. All right, so the last example that I'll show is this TSG, so a time signal generator. So this is a specialized toolkit as well, and effectively what it lets you do is take test data that you have. So if you have some test table and you're measuring some output signal, then you essentially reverse engineer the input signal from that output signal. So I really like this animation. Basically, if you're measuring something on one of these blades, you can feed that to RecurDyn and then convert that to whatever input signal is necessary to generate it. And then by doing that, you can measure more things in simulation than you can in test. But oftentimes you aren't sure what inputs you need to put in the simulation. So you can sort of work the problem from both ends by doing physical testing and then applying that to a simulation model where you can take cross sections in the middle of a part and things like that. And then obviously do a durability analysis, which you couldn't really do physically for an entire model like this. Yeah, and this is sort of just more of the same. I mostly just wanted to mention that that possibility exists. Then we do have one other question. Do you really use plastic strain amplitude in strain life fatigue? Um, yeah, so I think this varies a little bit based on the correlation you're using. Um, so there's multiple different correlations, and that's one of those things that you want to make sure for a given correlation you're operating in that assumption space of that model. So I can't give a great answer there, but that's one of those things. Make sure that uh, you know the back end assumptions of the given model.